Today we're doing question 3 for chapters 31 to 32. Question 3. Homework. Alright, and this will be talking about power in alternating currents. So, let's get this out of the way. Alright, so we'll start off with part A. Part A is going to say, in operation, an electrical toaster has an RMS current of 3.95 amps. When plugged into a wall socket with RMS voltage of 1.20 times 10 to the second volts, find the toaster's average power. So, the average power is given to us that P is equal to the power average to the voltage RMS multiplied by the current RMS. Because as these two will multiply together, it would give you what is the power that they're both giving out, which should technically make it, when graphed out in a current, these two are the voltage and current. This one should be bigger than both of them as it's both of them multiplied together. So we're going to input the values given to us, really simple, which will then be voltage of 1.2 times 10 to the second volts times 8.95 amps is equal to, calculator here, 0.95 times 1.2 times 10 to the second, which is 474 watts. It will be in wattage. 4 watts. That's for part A. Now part B. It's going to ask us what is the maximum. Now the maximum of the power is simply just 2 multiplied by the average. Really nice and simple. That's technically power average of 2 different things are then divided by 2, because VRMS would then be V squared 2 times I squared 2. So we just do it by 2, multiply that, so it's just going to be 2 times 474. 2 times 474 gives us 948. So 948 watts is our maximum power. For part C, we have to find the total toaster's resistance. And for that, since we have a voltage and current, we can simply just do our formula of V is equal to IR, and then just divide by I. So R is equal to V over I, where R will then be equal to the voltage RMS over the current RMS. So then we'll just have 1.2 times 10 to the second voltage per 3.95 amps. 1.2 10 to the second 0.95. It's going to give us, run it over to 30.4 ohms. It'll be 30.4 ohms. All right. So then moving on to the next steps. And then have part D. So here, we're going to have an LRC circuit. And as a source with a voltage amplitude of 35 volts, angular frequency of 1.3 times 10 to the third readings per second. The resistance will be 275 ohms. The inductance is 82.3 millihenry. And the capacitance is 1.1 microfarad. So to find the inductive and capacitive resistances for part D. So we're going to have an alternating current here. It's going to be dishing out 35 amps. Well, its amplitude is 35. And then we're going to have our resistance here. Try this out. first our resistor, then our inductance, and then capacitance. 275 ohms, 82.3, and then 1.1 farad. All right. So it's going to be asking us to find the inductive and capacitive resistances. So we have to find what are each the different phase vectors for them. So on a graph, during this alternating current, each and every single one of them is going to have a different kind of movement. Each range in some different way as the current is moving through all this. So we have to find what is the vectors of each of these different phases that are moving through. So for our first one, which would be our inductance, we just do X of L is equal to, find X of L, it's equal to our angular frequency multiplied by our inductance. So it's going to then be our angular frequency, which is given to us as 1.3 times 10 to the third radians per second, multiplied by our inductance, which for that one, 2.3, we're going to just move it to 10 to the negative 3, just to make it normal Henry. So we'll multiply those two together and we'll get our inductive versus reactant. Yes, reactances. So 1.3, don't forget parentheses, 1.3 times 10 to the third times 2, 2.3, 10 to the negative 3. That's going to give us 106.99, which we'll round over to 107 ohms. These will all be in ohms as the resistances to the circuit. And then for X of C, this one will then be angular frequency over C, because this one is inversely. The first one, was the reactance of the inductive, is directly proportional, while the other one, X of C, which is the reactance of the capacitive, is inversely proportional to the capacitance. So let's read 1 over, so let me just read 1 divided by the 1.3 times 10 to the third radians per second, multiplied by 1.1, and then we will then bring that to normal, which will be to the negative 6 farad, just to keep things symmetrical, and we'll multiply that together. So we're going to have this right here, it's a fraction of 1 over 1.3 times 10 to the third, multiplied by 1.1 times 10 to the negative 6. And that will give us 699, which we can just keep at 699 ohms. 699 ohms. And that's going to be answered for part D, which is going to be asking for these two right here. So move on to the next page. And then we'll do part E. Part E. So now we have to find the phase angle of it all. So we know that the phase angle is going to be tangent. Tangent phi is equal to our inductive reactance minus our capacitive reactance, our reactions flipped around. So these are subtracted by each other. And then it'll be divided by the actual resistance to 75 of the resistor, which I could just say R. So it'll be this formula right here. And we have to find this right here, which is going to be our phase angle. To the angle at which the phase, which the graph and the different phases in which it'll be moving back and forth, back and forth. All right. So we found our x of L, which is equal to 107, and our x of C, which is equal to 699. And we know that our resistor is 275 ohms. So here we'll just do tangent phi, so that equal to R107 minus 699 all over 275. 107 minus 699 divided by 275 to this negative 2.15. Now we're not done yet, because if we're trying to find the angle, we're going to try and find the inverse. And look at this is it's either arctangent of this part, or I like to always just do tangent -1 inverse. So I write it. Same thing as arctangent. So we'll just do arctan of that. So, and then my answer that I got. So that should give us negative 65. We'll round it over to 65.1. So our phase angle is negative 65.1 degrees. And then for part F, it's going to ask us, what is the power factor of it all? Now, power factor is going to be pretty much P. That's how you write P of F. It's going to be just the cosine of the angle, which is our power factor. So it's real simple. We're going to just put in cosine of 65.1. Let's write it as 65.1 degrees. Put on a calculator and we just find the power factor. 5.1. So our power factor is 0.42. 0.421. Your power factor. Let's keep moving on. And now for part G. Now, part G, for the circuit in the preceding problem, so we're going to keep using the same values that we solved previously. We have to find the impedance. Now, impedance, C is equal to the square root R squared plus XL minus X squared. Now, the impedance is pretty much the vector sum. Well, so vector sum would be like the Pythagorean theorem where everything else has to get out of square rooted. But I know that the XL minus XV, they're kind of on the same thing. So they need to be subtracted so that it's both same angle. So then we get our vector sum here. So we'll have square root of our 275 ohms, which we had given to us. And then what we found of x val, which is 107 ohms, minus 699 ohms, which is our other one for capacitance, all squared. So first we'll do 275 squared. 275, 625 minus, actually plus. So, and then we'll do 107 minus 699, and then square that answer, and we'll get 35, or this number right here, 350,464. Add that by our 75, 625. That's our answer, and then we're just going to square root all of that. So our final answer should be 652.7. You can round over to 653 ohms for impedance. There we go. So that's part G. And then for part H, part H is going to ask us for the current was for the preceding problem, we gotta find the current amplitude. Now we already have, we know that V is equal to I times R, so for finding current, just divide by R. So our current is equal to V divided by R, and we already know our amplitude for voltage. It's going to be 35 volts. And then we just figured out what this is. So pretty much the impedance is the total. And we just figured out the total resistance would be 653. So 653 ohms. So from there we can then do 35 divided by 653. And that will give us 0.0536. Let's run over to 536 amps. And that will be our answer for part H. And then for part I, moving on, this is going to be for the circuit. It's the same problem, same stuff. We're going to find the average power delivered to the resistor. P times AV. Now we don't have the voltage RMS or the current RMS, but we do know that it's also equal to the voltage times current. And since current is pretty much, or voltage is just current times the resistor, we'll just take these two and multiply them together. So then we are left with current squared times resistance is equal to the average power. And then it should also be a 1/2 as well. So 1/2. So we'll put this all together. So that'd be 1/2 of 0.0536 amps squared multiplied by our resistance of 275 ohms. So then do 1/2 times 0.0536 squared times 275. And that's going to give us our answer of 0.3395. So it's the average power is going to be 0.395 watts. So what's next page? That's the answer for part I. We go for part J. Alright, so the power factor of an LRC circuit is 0.8. And the frequency is 1.3 times 10 to the 4th radians per second. The inductance is 7.5 millihenries. And the capacitance is 0.44. New farad. Find the inductive and capacitance reactance. So this is like how we did in the last parts where we found the X of L and the X of C. Since we're given already, we know that angular frequency, the one is the inverse, angular frequency times capacitance, so it's just angular frequency times our inductance. So it would be 1.3 times 10 to the 4th radians per second multiplied by our 7.5, which will run over to 7.5 times 10 -3 henries. And then I'll have this one there as well. 1.3 times 10 to the 4th per second multiplied by our 0.44 times 10 to the -6 farad all over 1. That's how you set it up. And 10 to the 4th times 7.5 times 10 to the negative 3rd. And that should give us 97.5 ohms. So we 1 over 0.3 times 10. Make sure it's in parentheses here. Times 10 to the 4th times 0.44 times 10 to the negative 6. That will give us 174.8. Let's do 175 ohms. Okay. And then for part K, it's going to ask us to find the phase angle, which we know is tangent phi is equal to XL minus XC over R. But the tricky thing is that we haven't been given what our resistance is, so we can't figure it out using this formula. But we are given what the power factor is, and if we remember that power factor is equal to the cosine of angular frequency for the phase angle, then we know that pretty much 0.8, which is our power factor, is equal to cosine phi. So all we have to do is just inverse that. So cosine phi is equal to cosine, or arc cosine, of 0.8. And that will give us what our angle is. So 0.8. That should be 36.86, which is over to 36.9 degrees. Perfect. So then for part L, then we're going to find the resistance. You know, since we have all that, then we can find the resistance. Because from this formula, what we'll just do is just reverse everything. We're going to multiply our R to the other side, so it's with our tangent phi. So L minus XC, and then we're going to divide by our tangent phi, so that cancels out, and then this is on this side. There you go. So we're going to pretty much use this to then find our resistance. So it's going to be equal to our XL, which is 97.3 ohms, minus 175 ohms, all over tangent of 36.9 degrees. Just throw it all into the calculator. So we have 97.5 minus 175 divided by tangent of 36.9. And that's going to give us give us 103 ohms, and that'll be our answer. So answer is going to be 103 ohms, and that's our resistance for the circuit. All right, that is all the parts. Thank you very much.